Okay, so today we're going to be looking at applications of electrolytic cells. So what is an electrolytic cell? Does anybody remember? Right, so electrolytic cells, so just as a quick review here, they require energy. And so essentially what's happening in an electrolytic cell is you are taking electrical energy and converting it into what type of energy? Chemical energy, right. So these require energy, so the total potential net of the cell is positive or negative? Negative, right, because it requires energy. So it's going to require some sort of negative voltage in order for these cells to run. Pretty much everything else is the same in terms of, where reduction is happening, where oxidation is happening, the transfer of electrons from anode to cathode, that's still the same. Anions move towards the anode, cations move towards the cathode, that's still the same. But when I label the cathode in a voltaic cell, I label it as the positive side. In an electrolytic cell, it's labeled as what? The negative. Why is it labeled as negative? The Ra is above the OA, and because we attach it to the negative side of the battery, we call the cathode the negative part in this place. And that means the anode in a electrolytic cell would then be the positive. Everything else is pretty much identical to voltaic cells, except for kind of these differences. Cations still go towards cathode, anions still go towards the anode, electrons still travel from anode to cathode, all that stuff is still the same, just this stuff is different. So we're going to go look at some applications of this. So the first thing you need to know here, if you're following along in the notes, is what's called the chloride anomaly. And so this occurs in the electrolysis of solution containing the chloride ion. And so what does electrolysis mean? So an electrolytic cell requires what? Energy. And so electrolysis is like when you apply electricity. So, applying electricity. So the chloride anomaly occurs during the electrolysis of solutions containing chloride ions. And so in these situations, usually water, so if I put like salt water, just salt water, I guess, together, so sodium chloride and water together, what you would think would happen is water would be the SOA, water would be the SRA. But that actually doesn't happen, because what happens is the chloride ion reacts preferentially with water. And so that's why this is called an anomaly, because what's going to happen is chloride will slip below water on your SRA and actually react preferentially to water. Okay, that's why it's called the chloride anomaly. You have to memorize that. There'll be a question or two on my test. There's always a question on the diploma on the chloride anomaly. And so kind of what this means, so you guys, there's only a few things to copy there. So if I'm looking at my data booklet, what's happening in this case, and this only occurs when you have electrolysis. You're adding electricity to a water that has chloride ions in it. So this half reaction, what it would do is it actually would just slip right below and this water reaction right here, and it would come right here. Okay? And so I'm looking at the SRA, and so then the chlorine ions act as the SRA rather than water. Okay? They will not ask you to figure out the voltage of this, because that's not going to have the same voltage. You would have a lower voltage, obviously, in that scenario. But you just have to realize that, okay, chlorine would actually act preferentially to water in this case. So it's actually a pretty important chemical process in terms of industry. 95% of the world's chlorine and 100% of sodium hydroxide is created through this process of adding electricity to salt water. And so there's kind of the reaction. If you add electricity to sodium and water, you get chlorine, which is a gas, hydrogen gas, and sodium hydroxide. And so for example number 4 here, it says, write the equations for the cathode and anode of the net cell reaction. Good. Okay. We left off here. Okay. So write the cell reactions that occur at the cathode and the anode, and the half reaction. So essentially, you're never going to look at the reactants, and so a few people are doing that when they write their half reactions, right? I don't include any of this because that's not what's present when I first start my reaction. I can only write things that are on my reactant side. As well as when I'm writing that half reaction, I can't start off with hydrogen gas as a reactant in my half reaction because it's not present to start off with. So if I look at what's present in this cell, I have sodium aqueous ions because this is ionic, so it would break apart into its ions. I would have chlorine ions, aqueous, and then I have water, which is a liquid. And so I have to go look at, on my table, what's an OA, what's an RA. So this is an OA and an RA. Sodium metal is what I don't have my table. Sodium, no, that would be a RA. No, sorry, this is an OA, and this is an RA. So water is the strongest OA, and if it wasn't for the chloride anomaly, it would also be the SRA. But in this case, because chlorine slips below here, we actually use that as my SRA. Okay, so you have to remember that when you have chlorine and water reacting together. And so this is going to be my SRA. So I would write out those two half reactions. So my first half reaction is when water is a OA, it's pretty low down. It's so H2O, 2H2O as a liquid, reacts with 2 electrons to produce hydrogen gas and 2 hydroxide ions. So that's my first reaction. The second reaction would be from that chlorine reaction, so the anomaly. So remember, I'm writing the reaction now going from the left to the right. I'm writing the oxidation reaction. So I would take my chlorine, so 2Cl negative aqueuses are reacting with, or react to produce chlorine diatomic gas plus 2 electrons. And so pretty nice reaction, 2 half reactions. I don't need to multiply anything, right? My electrons are the same. And so I would just summarize here in terms of what's happening. So 2 waters, liquids, are reacting with 2 chlorine negative aqueous molecules to produce chlorine gas, which is diatomic, hydrogen gas, which is diatomic, and 2 hydroxides aqueuses. Okay, they won't ask you what's the total cell potential for this, but they will just say, like, what's going to be that total reaction. And you have to realize that chlorine is kind of a special case in that one. Okay? If there was some other SRA, so if you had cadmium metal or nickel metal in there, those would react as the SRA. The only time that this matters is when you have a competition between chlorine and water for the SRA, and in that case, that's when chlorine will move down. Okay. So in Edmonton, there's a plant that actually does this, and it takes a huge amount of electricity because they're pumping out massive quantities of chlorine, sodium hydroxide, and hydrogen gas. So they are pretty much just taking salt water from underground deposits, pumping it up, pushing it through these electrolytic cells, and getting the refining of hydrogen, chlorine, and oxygen. So hydrogen would be used to, make gases, crack petroleum, ammonium, hydrogen peroxide, margarine. Who knew? Not me. Now I do. Chlorine is used for, obviously, it's in pools, right, to disinfect it in water. And then sodium hydroxide is used to make cellophane, pulp, paper, detergents, all that kind of stuff. So very important chemical process. And there's the reaction we just looked at. Chlorine, what does that say? H2O, the transfer of electrons from H2O. Alright, so the next thing we're going to look at is electrolysis of water, as well as just like electrolysis of like what happens when we add electricity to different types of electrolytic cells. First one is just like the electrolysis of water. So I take electricity and I add it to water. Now, if it's salt water, is this reaction actually going to occur where I break water down into hydrogen and oxygen? Why not? Pardon me? Well, then, so if I had salt water as opposed just to pure water, I would end up with a chlorine anomaly. And so chlorine would be reacting. I'd be creating chlorine gas. If I had pure water and I add electricity to it, I should be producing hydrogen and oxygen, right? That's what electrolysis is. So again, just that chlorine alkali shows that the predicted reactions like the SOA and SRA aren't necessarily always going to happen. So when water is subjected to electrolysis, water molecules are oxidized at the anode and other water molecules are reduced at the cathode. If the system is operating in standard conditions, we should see essentially the net cell, which is when you take 2 water molecules, you produce double the amount of hydrogen compared to oxygen. And the voltage for that would be the same. There was a question in your homework 12, if you did that on like the electrolysis of water. It gave you a whole bunch of stuff, and it ended up that nothing else reacted except for the water. So essentially you would have been undergoing the electrolysis of water, producing hydrogen and oxygen gas. You don't have to. I mean, if you want to write it out, you can. I think that you should be able to figure it out. It's up to you. Okay. The system is acting in non-standard conditions. Water is a very poor electrolyte, and there is gas production at both electrodes. As a result of these factors, a considerable overpotential must be applied to get the system to operate. So it's essentially saying, like, water really doesn't want to decompose, and so even though it says that this is negative 2.06 volts, you actually have to apply more potential energy, so more than 2.06 volts, in order to get the system to operate. We might not get it to operate otherwise. Sometimes, though, if you add too much electricity, you'll change what's going to react, as we'll see here when we look at electrofining of metals. Okay, so the last thing that we look here in terms of application for electrochemical cells is actually the production of elements. And so a lot of elements that we have don't occur naturally, right? Like, I guess aluminum is one of the few that does, but like lead, so all the ones on there, sodium, potassium, lithium, calcium, magnesium, most of them are not found commonly in nature, so they occur as like an ore. What's an ore mean? If I have like a piece of silver, I got a piece of silver ore, nickel ore, what is that? Just like a chunk of it. Is it pure? No, it's impure, right? There's like other metals in there, there's oxygen in there, like it's not a pure metal. And so what we need to do is undergo electrolysis to try and refine the metal and get a pure metal, right? Sodium, if you look at sodium, like sodium doesn't exist really naturally. I have sodium in the back and it's stored underneath oil, right? That doesn't really occur out in the world. So in order to have this, we have to undergo electrolysis to purify metals if we want them. There's kind of 2 things to look at here, electrowinning and electrofining. Electrowinning is when you reduce metal cations from molten or aqueous electrolytes at the cathode of an electrolytic cell. There's a few things that I want to write down, but I'll kind of highlight them as I go through it. So here's an example of a question that talks about production of metals, or production of elements. So strontium chloride is melted in an electrolytic cell with inert electrodes. The products are chlorine gas and strontium metal. Obtain a net reaction. And so probably what's happening here is all that we have here is strontium chloride. So strontium would be 2 plus aqueous ions and chlorine, aqueous. As soon as I see melted, it means that they're not actually putting this in water and they have an electrolytic cell. They're actually taking that metal and heating it up as hot as they can get it. And then what's going to happen? So what would happen here, there's only 2 things that can react, right? And so strontium has to be my SOA, and this has to be my SRA, because there's only 2 possible things here. And even if I add water, it would kind of mess this up in terms of the chlorine anomaly, so that's why we're not adding water to this. And so what would happen is the strontium metal would, gain 2 electrons to become strontium solid, and the chlorine 2 chlorine ions would undergo oxidation to become chlorine diatomic plus 2 electrons. And obviously that's a pretty easy one to summarize. Strontium, oops. I'll get out of here. SR. You don't like me? SR2 plus would be reacting with 2 chlorine negative aqueuses to produce strontium solid and chlorine gas. Right? And so water is not included in this because it's melted. If it was, then I have a chlorine anomaly, and then this reaction that I wanted to happen, I guess it would still occur, but it would be a chlorine anomaly. Okay. Same kind of reaction here, right? So if I have lithium is the least dense of all metals, it's a very strong Ra and can be produced from electrolysis of molten lithium chloride at a temperature of 605 degrees Celsius. Its melting point, that's the melting point of it. And so what equation would occur at the cathode, what equation would occur at the anode, and then write the cell reaction. Same thing. So if I'm going to write out what reacts here, this is lithium. Ooh, that's a weird Li. Lithium is 2? Lithium is 1. 1? Yeah. Lithium positive, chlorine negative, aqueous. Do I include water if I'm writing out what's reacting here? No. I mean, it's happening at 605 degrees Celsius anyways. What's going to happen to water at that temperature? Vapor, like way before 605, right? So it's not even possible. So lithium aqueous would be reacting with 1 electron to become lithium solid. And then chlorine, again, 2 chlorines is producing chlorine gas and 2 electrons. And I'd have to double that. So 2, 2, 2, cancel out and summarize. It would still react. Fluorine's extremely reactive, but I have no idea. Lithium is reactive, but it's not nearly as reactive as. There's a thing about aluminum here. Third most abundant element on Earth. In the early 1800s, it sold for more than gold. Pretty interesting. Just comes down to saying that it's hard to make aluminum through electrolysis. It's hard to just apply a whole bunch of heat and break down aluminum because its melting point is 2072 degrees Celsius. And so you have to have an intermediate reaction in this cryolite to be able to produce it. Something I'm too worried about. But you do have to know this electrorefining, which I think is on the last page there. So electrorefining uses an electrolytic cell to obtain a high-grade metal at the cathode and an impure metal at the anode. So you have to know what goes where in these cases. So a high-grade metal at the cathode and an impure metal at the anode. And so essentially what would happen is if I take like a big piece of copper, or like impure copper, I put that at the anode and I apply electricity to it, assuming that the electrolyte is the right electrolyte, I can essentially start decomposing that ore to refine it to get pure copper, and then whatever other elements are in there will kind of sludge off by themselves. And so here's a good example. And so if I'm trying to refine copper, I take the impure copper, I put it at the anode, and I take a very high percentage piece of copper and put it at the cathode. This has to be pure copper in order for this to work. And so if I apply electricity to it, essentially what's going to happen is this impure copper ore is going to start breaking down. The electrons will travel to the cathode, and the copper ions that are in the solution, as well as the copper ions that are breaking off of that impure ore, will start attaching themselves to the pure piece of copper. And so that's how they gain pure copper or pure silver or pure whatever it is. And everything else that was part of that ore will start just like sloughing off towards the bottom, precipitating. Okay, so here is a question. So an impure sample of lead containing trace amounts of gold, silver, copper, cobalt, nickel, iron, zinc, and chromium. And so the first one says, at which electrode should the impure sample of silver, that says lead, and then this says silver, so this should say silver, sorry. So at which electrode is the impure sample of silver going to be placed? So do I want that impure piece of silver to lose electrons, or do I want that impure piece to gain electrons? Lose electrons. So I'm going to place that large impure silver ore at the anode. What material then should my cathode be made of? If I'm trying to get this piece of silver to become pure, what needs to be at the cathode over here? A piece of pure silver. It doesn't need to be a large piece of silver, but it needs to be silver in order for me to start depositing other silver onto that. Otherwise, I start depositing a metal onto another metal, and then they're mixed together, and then I don't really refine it at all. It's just added on to something else. What should be the solution in here? I have to have what in there? I have to have silver ions in here in order for this to, break off and make sure I have enough silver ions to add it onto here. And so you probably want like AgNO3, because nitrate's not really reactive. I don't really want to put chlorine in there, ideally, just in case I add a certain amount of electricity and things change, or once I run out of things to react. Doesn't get in the way. Identify all the half-cell equations that would occur in the electron refining and identify at which electrode they would occur. And so at the cathode, what reaction is happening, or what would I be producing at the cathode? I should be producing Ag solid, yeah, which means that I'm taking the silver ions and adding electrons to it, producing silver. At the anode, then, I have that impure piece of metal, which we're assuming would be soluble in water, so what would be happening at the anode is like silver would be breaking down to produce silver ions and an electron in water. But it would be more than just silver breaking off of that ore. What else would break off? The rest of the other elements, right? And so it said, what else does it say is there? It says like nickel. So nickel solid will be becoming Ni plus and 1 electron. Nickel 1 or 2? Mm-hmm. And I could have a whole bunch of other reactions there. Pardon me? Yeah, if you get a gold ore, yeah, you'd have to refine it. Gold can be pure. Identify any elements that will be included in the sludge. So the sludge is going to be all of this stuff here, right? The nickel, the cobalt, the iron, the zinc, all of those things would be just sloughed off and hopefully not reactive.
So it'd be solid into
Pardon me?
It'd be solid into like an ion, for all of the stuff.
Yeah, they would eventually just end up like precipitating out in the bottom, yeah, like you can see there.
Did you never flip
that? No. What's the minimum voltage that will be used in this cell? Well, realistically, if I have this reaction minus this reaction, the voltage for that reaction to actually occur should be close to 0, according to this data booklet. But we're not happening under those conditions, so you probably have to add a little voltage in order for this to occur. So I was like Googling it because I was like, I just can't find a number that's giving me. And so like in the process of creating copper, like electrorefining copper, They only need about 0.15 volts for that cell to run. But it's occurring on a large scale, so you're going to need more than just 0.15 volts, as well as it's occurring over a longer time. What's the maximum voltage? Now that depends on what's happening. If you add too much voltage, then you're going to have these other metals reacting that you don't want to react if you're trying to purify something. And so the last thing that this can be extended into is electroplating. And I don't know if you actually have this, but just something to know. So electroplating is the process of coating steel with a more desirable metal. And so if I take, a piece of steel and I want a chrome bumper, they just take that piece of steel and they dip it in to a chromium solution that has electricity being applied to it. And if it's under the right conditions, it will deposit on the on whatever you're trying to put it on. So the object, you have to know this, the object being electroplated is at the cathode. It's the same thing as when we were electrorefining, right? Whatever I want to be pure has to go at the cathode. And the unpure metal would be at the anode. And so essentially what's happening is those, like chromium, for example, the chromium metal ions get reduced onto that. So the example here is just like they're electroplating a silver spoon, and so I've tried to do this like multiple times. It's like electroplate a copper penny and make it copper, like shiny copper again, and I can never get it to do it properly. But I think I'm probably applying too much of voltage, so it's not working, but I might try later. Alright, some old diploma questions. No, that's what okay, so if you're gone, homework 13, and if you're in England, you need to come back and tell me the most British thing you've seen. Otherwise, I'll know you didn't watch this and I'll hate you forever. Have a great Easter vacation.